Alright, chemists, in this lesson we are going to look at what are called quantum numbers, which essentially act as a set of coordinates for indicating where an electron is. There are four types of quantum numbers to know about, and they are denoted N, L, M sub L, and M sub S, and those refer to what's called the principal quantum number, the angular momentum number, the magnetic quantum number, and the spin number. And they each mean something, and it's very much related to the electron configuration that we looked at in the previous lesson. N, the principal quantum number, refers to the energy and size. And the rules for that are the possible values are any positive integer, 1, 2, 3, etc., up to, let's say, n. So when we were writing electron configurations for atoms in the previous lesson, and we wrote things like 1s2, 2s2, it's that 1 and 2 in the front of each of those sublevels that we were referring to. That's called the principal quantum number. The second quantum number, the angular momentum, L, refers to the shape. And that's if we're talking about an S, a P, a D, or an F. And for our purposes, we're just going to say if it falls into one of those sublevels, it corresponds to a specific L quantum number. If it's an if it's an S, then the L quantum number is 0. If it's a P, then it's a 1. If it's a D, it's a 2, and so on. It's very easy. The third one is a little bit tougher to describe, but it refers to the direction of the orbital itself. And this comes up when we're looking at the less symmetric orbitals, so namely not the s orbital. The s orbital is spherical and completely symmetric about the nucleus. But remember, those p orbitals have direction. They can be along the x-axis, the y-axis, or the z-axis, and we give them different quantum numbers. You can actually just relate it and think back to orbital diagrams. Let's say we're considering the 2p orbital system, which you could represent as just 3 horizontal lines. And if you have electrons in one set as opposed to another, we give them a different quantum number. It's always the middle one is given a number of 0, and then you go positive 1 and negative 1 as you go above and below that. That's the notation. You'll see what I mean when we look at some examples in a moment. And then the last quantum number refers to the spin number, and that refers to what's called the spin state. And this can either be an arrow up or an arrow down. And if it's an arrow up, we give it a positive 1/2, and if it's an arrow down, we give it a quantum number of a negative 1/2. And if you combine a set of quantum numbers, there's 4 for every single electron in an atom, you get a solution set to the Schrödinger equation. That's what these are. I'm not going to go into the mathematics of the Schrödinger wave equation, but it's very highly studied, and there's a lot of research about it, and it essentially is a solution set. A mathematical solution set is what the quantum numbers are. Now, there is something called the Pauli exclusion principle, and this says what we've actually already seen, that no 2 electrons can have the same exact set of quantum numbers. It's analogous to saying that you and another individual can't be at the exact same place at the exact time. Same with electrons, same way of thinking about it. If there's one already occupying a certain spot in an orbital, that's the only one, and that's denoted by the quantum numbers that you would have. So, let's take a look at some examples. The first one says, what are the possible values of L, the subshells, and M sub L, the orientations, if we're in the third principal energy level? Well, if you're in the third principal energy level, if N is 3, then you have to have the possibilities of L being equal to 0, L could be equal to 1, or L could be equal to 2. And that corresponds to the 3s orbital, the 3p orbital, and the 3d orbital, or orbitals, we should really say. And remember, there are 3 types of p orbitals, 5 ds, but only 1 s in the principal energy level of 3. So then those are our three possibilities for L, 0, 1, and 2. What about M sub L, the orientation? Well, there's only one possibility for S. There's only one type of S orbital in any energy level, so we give it a value of 0. And that refers to that one and only orbital in level 3s. But there's three types of p orbitals, and M sub L is -1, 0, or +1. And that refers to those three possible types of p orbitals. So what do you think would be true for the D set? Well, there's 5 of them, and they surround a center of M sub L being equal to 0. So we're going to go up to +2 and down to -2, and I'll list them in order: -2, -1, 0, +1, and +2. That's how quantum numbers work. So let's wrap up and just look at a more detailed example where we actually identify the quantum numbers for every single electron in an atom. We'll do a small atom. We'll talk carbon, which has a total of 6 electrons. And remember, carbon's electron configuration from our previous lesson would be 1s2, 2s2, and 2p2. Those are all 6 of the electrons. I'm going to go one further, and I'm actually going to draw a large orbital diagram for this. There's the 1s orbital with 2 electrons in it. There's the 2s orbital also with 2 electrons in it. And then there's the 2p orbital with 2 electrons in it. And what we could do is we can give a set of quantum numbers for each and every single electron in that atom. So starting with the first one, that 1s electron, let's zoom back into where we have electron 1. N would be 1, because it's in the first shell. Because we're in an s orbital, the L would be 0. And when you're in an s, there's only one type of s orbital, so M sub L would also be 0. Now, the first electron, if we go back to the orbital diagram, has an arrow pointing up, and by convention, that has a +1/2. So we get 1, 0, 0, -1, a +1/2 for the very first electron. Now, every single other electron in carbon's set will have at least one of those quantum numbers different. So that was the first one. Let's look at the second one. The first 3 quantum numbers are going to be exactly the same. It's still 1, 0, 0, but it's got an opposite spin state. It's -1/2. And we're satisfying the Pauli exclusion principle. No 2 electrons have the same set of quantum numbers. Now, what about the third electron? Well, the third electron is in the 2s orbital, so we're in energy level 2. We're still in an s, so L would be 0. M sub L, therefore, also has to be 0. And the first one will be a spin state of +1/2. The fourth electron, that's the 2s2 electron, so we're in the second shell. Still in an s, so it's 0 for L, 0 for M sub L, but -1/2 for M sub S. Now what about electrons 5 and 6? Now we're talking about these 2p electrons. So we're still in n equals 2, but L is now going to be 1 because we are in a p orbital. And think about what the next set of numbers would be. Remember, this goes from -1, 0 to +1, and there they are. So that tells us exactly what those quantum numbers are going to be. So electron 5 is going to be 2, 1, -1, and then +1/2. That's how you would designate electron 5 in the carbon atom. What do you think the last electron would be? Well, it's still n equals 2. We're still in 2p, so L is 1. It's M sub L that's different here. This is M sub L is equal to 0. That would correspond to one of the other of those 3 p orbitals in the same subshell. But M sub S is still +1/2. Okay, and we could do this for any electron in any atom. That's what quantum numbers are. For us, they simply act as a set of coordinates. Let's go one step further. Let's actually wrap up and do one of the homework problems on the back to just make sure we fully understand this. I'm going to zoom in on 15b, which asks us to figure out the maximum number of electrons in an atom that can have this set of quantum number restrictions. So, and let's just look at B as an example. B says that n has to be 5 and M sub L has to be +1. So if n is 5, we have the possibility of a 5 5s, we have a 5p, we have a 5d, we have a 5f. You actually also get one more energy level past that. There is also the 5g. Now that's just sort of an excited state for our purposes. We don't see ground state electrons in this, but it's a possibility just in terms of the quantum number restrictions. And I'm going to draw orbital diagrams for these just as horizontal lines. There's one type of 5s, there are 3 5p's, there are 5 in the d, there are 7 in the f. This is what we talked about in the previous lesson. Take a guess as to what you think would be in this G orbital, this excited state. There would be 9. It's odd numbers. 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then what are our m sub l numbers? Well, the restriction says that it has to be positive 1. So I'm going to zoom way in and write the m sub l's below each of those. Well, the s is just 0. The p's has 3 possibilities, -1, 0, +1. The D, -2, -1, 0, 1, and 2. The F, -3, -2, -1, 0, 1, 2, and 3. Guess where it goes down to for the G's? It goes to -4. -3, -2, -1, 0, 1, 2, 3, and 4. So our restriction is that n is 5. All of those satisfy that. But this m sub l being only +1, that only hits that specific 5p orbital, that specific 5d, that 5f, and then that 5g. And each of those has the possibility of holding up to 2 electrons. So I could have 8 as the answer to this question, which satisfy those quantum number restrictions. If we wrote out the quantum numbers for all 8 of those electrons, they would have those 2 specific quantum numbers. Spin states would be positive and -0.5, and then the L quantum number would respectively be 1, 2, 3, or 4 for the different type of orbital. So that's how quantum numbers work. They exist as a set of coordinates, essentially, for where electrons are. No 2 electrons can have the same set of quantum numbers in the same atom. And then we'll use this to move forward and look at periodic trends and what we can use to describe the properties of the atom and eventually how they react with each other.